Pulley and block problems. Everyone hits them. You just can't solve them fast unless you memorize a bunch of formulas, right? Right? Wrong. In this video, I will take you step by step through these 5 carefully designed problems to show you how to crack any pulley block problem in seconds with pure logic, no formulas. Ready? Let's jump right in.
Let's start with the first problem. The figure shows two blocks, 2 kg and 6 kg, connected by an inextensible string and being pulled apart by the given two forces of 20 Newton and 60 Newton. We are supposed to find the acceleration of the blocks. Now, if you notice, I have used the same variable to represent the acceleration of both the blocks. I can do that because the string here is inextensible. Since the length of the string cannot change, then the two blocks are forced to move together. That is, if the 6 kg block were to move to the right by 1 centimeters, the 2 kg block would be forced to move to the right as well by the same distance of 1 centimeters. This is called constraint. Whenever there's constraint in a given problem, we have a huge advantage. The advantage is that now, since the blocks do move together, I can simply consider the entire thing as one single system. This allows us to consider them not as two blocks but as one single block of 2 plus 6, that is 8 kgs. And now we can apply the same two forces of 60 Newton and 20 Newton on our block. And this 8 kg block is to move with the same acceleration a. Now you can see how simple my life is because it's just one block. So let's take the rightward direction as positive and apply Newton's second law, that is F equal to ma. The rightward force 60 Newton would be taken as positive, and the leftward force, which is opposite to our chosen direction, would be taken as negative. This would be the sum of all the forces acting in the horizontal direction. This should be equal to the mass of our system, which is 8 kgs, multiplied by the acceleration, which is a. 60 minus 20 gives me 40, equal to 8a. That gives me a equal to 40 by 8, or 5 meters per second square. That is the acceleration. Let's look at the second problem now. The figure shows these two blocks, 9 kg and 1 kg, connected by a single string that goes over a pulley. Upon seeing this problem for the first time, many of my students think, and I'm sure that many of you must be thinking this too, that it's just a 1 kg block trying to pull a 9 kg block. So the 9 kg block would just not move. But if you think about it, the force that is trying to move this system is gravity, which acts on this 1 kg block. But there's not really any force that's trying to stop this system. So the system would, of course, move. And we can, of course, use a Newton's second law to prove that the system moves with some acceleration. Let's first look at the long and boring usual method to solve this problem. The standard approach is usually to make the FBD or free body diagram of each of these blocks. Let's try to do that. Let's look at the 1 kg block first. Let's think about the forces that act on this 1 kg block. Well, I can think of gravity, which acts downwards. And I can think of a tension that's there in the string. Let's call the tension T, and the gravitational force, which is the weight of the block, is given by m times g, that is mass, times the acceleration due to gravity. For the sake of simplicity, let's take g as 10 meter per second square instead of 9.8. The mass is 1 kg and g is 10. So the weight of this block is 10 newtons. If I take the downward direction as positive, I can write the equation again, sigma F equal to ma. By the way, the sigma here means summation, that is simply the sum of all the forces. Taking downwards as positive, this 10 Newton force is a positive force. So we would have positive 10 minus t, because t is opposite to the direction of our chosen positive, equals m, that is the mass of the system. Since we are only talking about the 1 kg block, we should take the mass of only the 1 kg block. multiplied by the acceleration a. You would again notice here that I'm using the same variable a for the acceleration of both the blocks. The reason is still the same, that they are connected by a string that cannot extend. If the 1 kg block moves down by a certain distance, the 9 kg block would be forced to move by the same distance but horizontally. That means the acceleration of the 1 kg block downwards is the same as the acceleration of the 9 kg block in the horizontal direction. Now let's make the free body diagram of the 9 kg block. The only relevant force that I can see on the 9 kg block is the tension. There is, of course, a gravitational force on the 9 kg block downwards, which would be m times g, so 90 newtons. However, there would be a counter force called normal reaction, which would simply balance this 90 newtons. So we need not worry about it if you're only talking about the horizontal motion of this block. So considering only this tension and taking rightward direction as positive, I can again write F equal to ma. So the only force is T equals the mass, which is 9, times the same acceleration a. This makes my second equation. Let's add the two equations up, and you would see that the minus t would get cancelled with the plus t. So I'd have a 10 on the left hand side, and on the right hand side, I have 1a plus 9a, that is 10a. So I have 10 equals to 10a, or a equal to 10 by 10, or 1 meter per second square. This is the acceleration we were looking for. Well, even though this method looks quite short, you would see that this problem can be solved using a much shorter method. So now, let's look at the quick and sneaky trick that I'm going to use to do the same question in just one equation. If you think about it, what is really moving this system? Like we discussed, it's just gravity that's trying to pull the 1 kg down. However, there is no force that's trying to stop it. So all I'm going to do here is take that string here and just straighten it up. The diagram that you will get would look like this. And now this problem becomes extremely simple because this is just the same as our first problem. So it's just a 10 Newton force acting on a system of mass 10 kgs. So we know that the acceleration would be the force over the mass, that is 10 over 10, which is 1 meter per second square. So you can see that we reach the same answer with practically no calculations. And I hope now it makes more sense that such questions can be solved in seconds. Let's look at the third problem now. The figure shows an Atwood machine. It shows two blocks connected by a string that goes over a pulley. The constraint in this problem is kind of similar to the ones that we have seen before. If the 6 kg block were to go down by a certain distance, the 2 kg block would be forced to go up by the same distance, meaning the acceleration of the two blocks would be same in magnitude but opposite in direction. If you want to solve this problem with your usual long and boring method, the method remains almost the same. You make the free body diagram of the 6 kg block and the 2 kg block. If you identify the forces, the force on the 6 kg block is 60 Newton downwards, that is 6 times 10, and a tension upwards. On the 2 kg block, we have a 20 Newton force downwards and T upwards. However, we can still use our trick in this problem simply by doing the same thing again. We take the string and we straighten it up. And when we do that, the resulting diagram looks like this. But wait, isn't this the same diagram as the first problem? So the answer must also be the same. Taking the rightwards positive, the acceleration A could be found by taking the net force, that is 60 minus 20, divided by the total mass of the system, that is 8 kgs. So 40 divided by 8, or 5 meters per second square again. So I hope you can now see how easy and fun this is. And if you have been watching so far, you're probably very serious about acing your exams. So I would highly recommend subscribing the channel. Let's go to the next question. The diagram of the fourth problem again shows two blocks connected by a string going over a pulley. However, in this diagram, the 4 kg block is placed on an inclined plane. Just like all the previous problems, we would first try to think about the forces that act on each of these blocks. On the 6 kg block, there is a gravitational force acting downwards, which would be 60 newtons because 6 times 10. And then there would be an upward force of tension. On the 4 kg block, we have a tension going up the incline along the string. We have a normal reaction due to the inclined plane, which is perpendicular to the inclined plane. And we have a gravitational force of mg, which is 4 times 10, that is 40 newtons. Now, since force is a vector quantity, we cannot deal with these three forces as is. We would first need to choose our positive x and y directions. The logical way to go about it would be to choose the direction up the incline as positive x axis and then the perpendicular direction as the positive y axis. We would see that this tension is already along the x axis and the normal reaction is already along the y axis, so we don't really need to touch them. However, this 40 Newton force of gravitation is neither along the x axis or nor y axis. Thus, we would need to break it down into components. For better understanding, let's draw it separately. So, this is the weight. Let's call it mg for now because I want to create a general formula for this. The x component would be going down the incline, so that is in the negative x direction according to our chosen directions. So something like this. And then the y component would also be towards the negative y axis. So you would make it like this. Now, if I want to resolve this mg into two components, I would use trigonometry. And to do that, I would require this particular angle. If you look at our previous diagram, if this angle is 30 degrees and our weight is vertical, so if I extend this line, you would see that I have created a right angle triangle. So if this is 30, then this angle should be 90 degrees minus 30 degrees, that is 60 degrees. That means this particular angle right here is 60 degrees. And if that is 60 degrees, that means this would be 30 degrees. That means this angle is same as the angle of incline. So let's call it theta for now. Now let's apply trigonometry. Let us call this component of the weight as fx because it goes in the x direction, and let's call this fy. As we know that sine theta is equal to the opposite over the hypotenuse, so it would be the side opposite to theta, that is fx, divided by the hypotenuse of the triangle, that is mg. If I cross multiply this, I get the value of fx, that is the x component of force, as mg sine theta. If this is sine theta, then of course, if you write the expression for cos theta, you would get fy as mg cos theta. Now, I would highly recommend to remember this for faster calculations. The side which is closer to theta, that is this one, would be cos theta. So this is how you can remember it. And then the side that we required, that is the force that goes down the incline, would be mg sine theta. So whenever you have any inclined plane, the component of weight that goes down the incline is always mg sine theta if theta is the angle of incline. This means that in our diagram, the value of this force that goes down the incline is mg, which is 40, multiplied by sine 30 degrees. And if you know the value of sine 30 degrees is half. So half times 40 gives me 20 newtons. Now, if I analyze this diagram again, I would see that there are two forces which are essentially moving the system. The 6 kg block is being pulled down by 60 newtons, and the 4 kg block is being pulled to the other side down the incline by 20 newtons. So if I apply the same trick again and I take this string and straighten it up, then we would see this diagram. Well, I don't know about you, but this looks quite familiar to me. If you think about it, it's quite similar to the first problem that we did. We have a 60 Newton force to the right and a 20 Newton force to the left. So the net force is 60 minus 20. And if I divide it with the total mass of the system, that is 4 plus 6 or 10, I would get 40 over 10, that is 4 meter per second square, as the acceleration of this system. Finally, the moment we've all been waiting for is here. Let's combine everything that we have learned in this video and try to solve this particular problem. The problem shows two masses connected by a single string going over a pulley. This time, both the masses are placed on inclined planes. Again, there is a constraint that if the 4 kg block goes down the incline by a certain distance, the 1 kg block has to move up the incline by the same distance. Thus, their acceleration is same. This acceleration is what we need to find out. So with everything that we have learned, let's think about the forces that act on the 4 kg and the 1 kg block. The only forces that we need to worry about in this problem are the components of the weight of the 4 kg block along the incline and the component of weight of the 1 kg block along the incline. And we have learned how to find their values. For the 4 kg block, it would be mg sine theta, that is 4 times 10 times sine 30 degrees, which is 0.5. So 20 newtons. For the 1 kg block, it would be mg sine 37 degrees, that is 1 times 10 times 0.6, because the value of sine 37 is 0.6. So 6 newtons. So again, just like all the problems that we have done, this particular problem can be reduced to the given figure. To find the acceleration of the system, we just do the same thing again. We take the driving force minus the force that's acting opposite to it, divided by the total mass of the system, that is 5 kgs, which gives me 14 over 5. Let's see a cool trick to divide by 5. I multiply and divide this expression by 2. The denominator becomes 5 times 2, that is 10, and the numerator is 28. So I have 28 over 10, or 2.8 meters per second square. That is the acceleration we were looking for.
And that is how you solve pulley and block problems. Pure logic, no formulas. In the next class, I will teach you a step-by-step method to solve any problem in dynamics. It's going to be even more important than today's lesson, so don't forget to subscribe. If this video helped you, give it a like. It lets me know what's working for you. Got a doubt? Drop it in the comments. Thanks for watching, and I'll see you in the next one.